Welcome to Domain 3, Section 3.5, Data Security. In this session, we will focus on protecting the data that powers AI, covering data, encoding, access, confidentiality, backup, and integrity. Why does this matter beyond the exam? AI creates a real tension. Boards want data unlocked so AI can use it, while security teams want it locked down. Understanding AI data security lets you give AI the access it needs without flinging the doors wide open, protecting the most sensitive data your organization holds. Let's frame that tension first. Privacy laws and data residency rules restrict how personal data can be used, yet leadership is now pushing security leaders to grant far more access so AI can exploit that data. The guiding principle through this squeeze is least privilege. Every system, identity, and process should get only the minimum access needed for its task, which sharply reduces the chance of data leaking out, whether by accident or malice. The first area is data encoding. Many deep learning models require raw data to be tokenized, broken into pieces and stored in binary files, and those files need the same access and encryption controls as any other sensitive file. Data can also be encoded into vectors, which are mathematical representations of text, images, or audio. These power the vector databases behind generative AI and semantic search, and they need not just access controls and encryption, but also careful management of the indexes that control access to them. The second area is data access, because AI aggregates data from many sources, and that concentration creates risk. Pulling everything into one central store, like a data lake, creates a tempting target, and during the transfer, the original access controls may not carry over. On top of that, data scientists exploring datasets can stretch the original definition of least privilege, and replicating data into central repositories multiplies the systems that must be secured and brought into compliance scope. The defense is to review the AI system's data flow, identify every store and user, and reapply access and network controls so data stays contained to authorized systems. The third area is data confidentiality, which can quietly erode if controls are not carefully designed. The catch is that training often requires data to be machine readable, and common tokenization methods work on clear text, so sensitive data may actually be decrypted during development. Emerging techniques offer hope here. Homomorphic encryption can let a model train on data without ever decrypting it, though its heavy computing cost limits used today. For now, the practical answer is compensating controls, limiting access to unencrypted production data, monitoring how sensitive data is used, and applying disk-level encryption for defense in depth. The fourth area is data backup, and here the priorities are surprising. Backing up training data sourced from elsewhere is often redundant, but the new artifacts created during development genuinely need protection. The processed and tokenized training data, the model weights, and the architecture definitions. There is a further reason to preserve data. Because generative models are non-deterministic, meaning the same input can yield different outputs, explaining their behavior is hard, so keeping copies of the training and testing datasets and the performance and bias results is essential for explainability. The fifth area is data integrity, which remains critical even though models are non-deterministic. Several scenarios threaten it: data poisoning that alters training data, model tampering that changes weights or parameters, and embedding tampering that skews results. Integrity can also break during routine data preparation, where the extract, transform, and load steps can introduce errors, so those requirements must be defined, documented, and tested. Additional safeguards include anomaly detection on training data, separating training data from production data, using validation and model ensembles, and hardening the model itself. Let's bring it all together. AI data security balances access against protection through least privilege. Encode and tokenize data behind encryption and access controls. Secure aggregated data and reapply controls as it moves. Defend confidentiality with compensating controls since training may require decryption. Back up the new artifacts like weights and processed data, and protect integrity against poisoning, tampering, and processing errors. You now know how to secure the data behind an AI system. Every important topic and idea from this session is covered in the multiple choice questions on RooCloud.com. Before you move on to the next session, work through the chapter-wise questions there, because these data security controls are prime exam material. Practice first, and then move forward with confidence. Thank you for watching, and I will see you in the next episode.